Alright, today we're going to start AC circuit analysis by looking at this problem that I have on my notebook where we have a sinusoidal voltage source of this function of time here, this cosine 12 cosine 500t. So 500, that's our omega, that's our source frequency. And since we don't have an angle here, the theta is 0. And we've got this sinusoidal voltage source connected up to a capacitor, as you can see, of 10 microfarads. Micro is 10 to the minus 6. Okay, don't confuse that with milli like some people do. Here's a 20 ohm resistor, and then this is a 3 millihenry. Okay, milli being 10 to the minus 3. So what I like to do with these problems is first write any sinusoidal voltages or sinusoidal currents that are given in the problem as phasors. So the phasor notation of the source voltage would just be 12, the amplitude bracket 0 degrees. Okay, because again, the phasor, you just leave out the frequency term. So we leave out the cosine 500t in our phasor notation. And then we weren't given the impedance of each of the elements, so that's the next thing that I like to calculate. So impedance of a 20 ohm resistor, like we talked about, is just 20 ohms, right? It's just purely real. Impedance of an inductor is j omega L, so that's going to be j omega is 500 in this problem, and then times 3 millihenries, which is 0.0003 henries. So that comes out to J 15 ohms. And then the impedance of the capacitor, well, that's minus J 1 over omega C. Alright, so if you plug in omega 500 and also the capacitor value of 10 microfarads and then take the reciprocal, you'll see this comes out to minus J 20 ohms. Alright, so we have the impedance of each of the elements. We have our source voltage and phasor notation. The next thing to solve this problem, and by the way, all the methods that we learned in DC, mesh current method, node voltage method, and also solving circuits with equivalence techniques and reduction techniques, that all still applies to AC. So we could solve this circuit with mesh, or we could solve it with node voltage method. You'll see in the AC portion of this class that I will all the time I'll just use reduction techniques along with equivalent impedance here instead of equivalent resistance like we had in the DC case. And the only reason for that, the only reason I'm not using node voltage method or mesh current method on these AC circuits is that in general with those methods you're going to end up with simultaneous equations that have complex coefficients. And not to say that that's difficult to do, but in a survey class like this for non-majors, I just think the AC problems that we're going to see that aren't going to be overly complicated. It's just as well just to solve it with reduction techniques. So the next thing I'm going to do in this circuit is I'm going to reduce it down to just the source along with a single ZEQ. So just like in DC circuits where we reduced all resistors down to an REQ from the perspective of the source, here we're going to get the ZEQ from the perspective of the source. So we start away from the source, and I'm going to start with these two here, and I'll label it ZRL. Right? ZRL is just the impedance of the resistor and the impedance of the inductor added together since they're in series. So this is just going to be 20 plus J 15 ohms. Okay, and then these two in series are in parallel with the capacitor, and then once we do that combination, that is ZEQ. Okay, so ZEQ is going to be product over sum with 20 plus J 15 and minus J20, which is the impedance of the capacitor. in the numerator, and we've got the sum in the denominator. Okay, so now you got to be able to do this complex math. If you go ahead and multiply up top, you're going to get a real part of 300. See, that comes from the j15 times the minus j20. 20 times 15, that's the 300. And then j times minus j gives you minus j squared. J squared, remembering that j is the square root of minus 1, so j squared is just minus 1, so minus a minus 1 is plus, so that's why it's plus 300. So you may have to review your complex math to make sure you understand that. And then the other term here is going to be minus j400, which is the 20 times the minus j20. So minus j400. Okay, and then the bottom we're going to have 20 real part, and then plus j15 and minus j15. That's going to give me minus j5. Okay, and what I did is I converted these into polar form. If you convert this into polar form, this top has a magnitude of 500. The angle is minus 53 degrees. And on the bottom, we've got a magnitude of 20.6. And we've got an angle of minus 14 degrees. Right, remember, to go from rectangular to polar, the magnitude, it's just sum of the squares square rooted. So 300 squared plus 400 squared, all square rooted, will give you the 500. And then to get the angle, it's just the arctan, or inverse tan, of the imaginary part divided by the real part. Alright, so you work out this division here. So 500 divided by 20.6 gives you 24.3. And then minus 53 degrees plus, or minus 53 degrees minus a minus 14 degrees. So minus 53 plus 14 gives you minus, or excuse me, yeah, gives you minus 39 degrees. Alright, and the units here are ohms. So that's our Z equivalent. So now with our Z equivalent, we can find this current right here, okay, what the source current is, just by Ohm's law, taking the source value divided by that Z equivalent. So, this should be deja vu for you, as far as if you think back to DC, this is exactly the same thought process as solving a DC circuit with this method, with the equivalence and reduction technique method that we learned earlier in the quarter. So you see that I for the source, okay, source current is just going to be the source voltage, which in phasor form is 12 volts at 0 degrees. And we're going to divide that by the Z equivalent of 24.3 at minus 39 degrees. Right, so this is voltage, this is ohms, that's a degree symbol there. Okay, and that comes out to slightly under a half or magnitude. It's 0.494. That's the magnitude of the source current, and then the angle is plus 39 degrees, right? Because we're going to get 0 minus 39, which is plus 39 degrees. So that's your source current. So in our diagram, this 0.494 current at 39 degrees, that's this current right here. Alright, because the current flowing through the source in this picture, it's going to be the same current flowing from the source in this picture. So now, when the source current gets to this connection here, where we have the capacitor and the resistor inductor in series, well, guess what? Just like in a DC circuit, this current's going to split. And we can find out how that current splits by using current divider. So just like in DC circuits, where you have current divider, where, okay, right over here, DC, Okay, remember current divider, general form is to get the current through a parallel resistor, you take the current flowing into the parallel combination times a ratio of resistances where Req divided by R, where R is the resistor you want the current for. Well, AC current divider, same form of equation, it's just you got impedance instead of resistance. So current through an impedance is the current flowing into the parallel combination of impedances, and now your ratio is ZEQ over ZEQ over R. Okay, so come back here. Okay, ZEQ divided by Z, where Z is the impedance that you want the current for. So to find the current, say, through the capacitor, we would have that IC, the current for the capacitor, is just going to be the source current that's flowing into the parallel combination of the capacitor and the resistor and inductor in series. So this is our current that goes out front. Okay, and then the ZEQ of the parallel combination just happens to equal the ZEQ of the source in this case. So that's the 24.3 at an angle of minus 39 degrees. Okay, and then the impedance of the capacitor goes in the denominator, since that's the impedance we want the current for, so that's going to be the 20 at minus 90 degrees. Okay, so now if we go ahead and work this out, you'll see that the capacitor current comes out to 0.6 at an angle of 90 degrees, right? Because see, the angles here, 39 plus minus 39, that's going to cancel out, and then you'll have 0 minus a minus 90, which is 90 degrees. Okay, and the units here are amps. Alright, so you see that's our capacitor current as a phasor. Now, another way to get the same answer is if you look back at the circuit here, since that capacitor is in parallel with the source voltage, they have the same voltage. So 12 at an angle of 0 divided by 20 at an angle of minus 90 degrees gives you the same answer. You could just use Ohm's law, where the capacitor current is equal to the voltage across the capacitor divided by its impedance, and you'd get the same answer. Now, this is the answer for the capacitor current in phasor form. Once you have an answer in phasor form, you can then go to a function of time by just putting in the source frequency. So you see, we could write now as a function of time the capacitor current as 0.6 cosine 500t, right, because that's our omega, plus 90 degrees. Okay, so you see this just drives home, hopefully, that our phasor notation is just a convenience, because it just allows us to do the analysis without dragging along this frequency term. See, I leave out that frequency term until I get my answer, and then once I have my answer, I can just insert it back in. And I could do the same thing here for the source current. The source current as a function of time would just be 0.494 cosine 500t plus 39 degrees. Okay, so we have the source current, we have the capacitor current. The next thing we could do is find the current through the resistor and inductor. Now we could use current divider again, where the only difference is that the impedance in the denominator of the ratio would be ZRL instead of ZC. But another way we could do it, and this is the same as in a DC circuit, well, I know the current flowing into this node, and I know one of the currents flowing out, right, the current for the capacitor here. Well, to get this current, right, that's also flowing out of this top node, I could just use KCL. So I could find IRL in this circuit. Okay, I could do IRL by just taking the source current and subtracting from that the capacitor current. Alright, because again, just like in a DC circuit, in an AC circuit, currents into a node have to equal currents out of a node. So you see this is going to be 0.494 at 39 degrees minus 0.6 at 90 degrees. Okay, and as you know, you can't subtract these vectors directly because they're at different angles, so we would have to break these up into the components, right? We'd have to convert the polar form here, magnitude and angle, into rectangular form where we have the real and imaginary components. So if you do magnitude times cosine 39 degrees, you'll get the real part of 0.38. And then if you do 0.494 times sine 39 degrees, you get plus j 0.31 for the imaginary part. And then here, the imaginary part is going to be 0 since you have cosine 90 degrees. And then for our imaginary part, see the real part would be 0 because of cosine 90. And then the imaginary part is just going to be j 0.6 because we got sine 90, which is 1. Okay, so now we just go ahead and combine these, and we get a real part of 0.38 and an imaginary part of minus j 0.29. Alright, so you see that would be the answer for IRL in rectangular form, and then you could put this in polar form. In polar form, this is just equal to 0.48 at minus 37 degrees. Alright? And again, you could write this as a function of time by just putting in the cosine 500t. So IRL of t would just be 0.48 times cosine 500t minus 37 degree amps. And you see we have all the currents now in this circuit. We have the source current, the capacitor current, and also the current through the resistor and inductor. So just like in a DC circuit, when you know current and resistance, you can get voltage by R times I. Well, in an AC circuit, once you know current and impedance, you can get voltage from I times Z. So as an example of that, if I wanted the voltage across the 20 ohm resistor, I would just take its impedance of 20 and then multiply times its current, which is, in this example, 0.48. Oops. Made an error there. I didn't put the angle in. So 0.48 at the angle of minus 37 degrees. And that comes out to a voltage across the resistor of 9.6. Right, because 0.48 times 20 is 9.6. And the angle is the same as the current through the resistor because they're in phase, so minus 37 degree volts. Okay, so we're going to do a couple more problems in the next couple of videos, again using AC circuit analysis, and hopefully if you don't already see it, you'll see eventually that solving these AC circuit problems, it's the same concept and thought process as solving a DC circuit. The only difference is we're dealing with vector quantities now, phasors, which are vector quantities that represent sinusoidal voltages and sinusoidal currents, and then impedance, that's generally a vector because it has a real and imaginary part in general.